Hi everyone, thanks for coming. So yeah, a bit of background in case you're not aware of Genomics England. We are a sort of state-owned company that's owned by the UK government, and we perform all the genomic sequencing for the NHS in England. So if you end up going to your GP for something that could potentially be caused by a genomic illness, so for instance if you have a rare disease that could have a genomic cause, your GP will recommend you for a whole genome sequence, right? So they will take a sample from you, that sample will come to us, we will do all that sequencing, and then we will get back a whole host of potential variants. Now the problem is, when you do that sequencing, you'll find that actually the average person has about 6.5 million variants in their genome relative to a reference genome, which is quite a lot, right? And potentially we're only looking for one of those. And if we try and narrow the scope a bit, there's only 700,000 of those variants that are going to be considered rare in the population. So we've already got things down quite a bit. 3,000 of those are likely to be predicted to cause a change in a protein. So again, we're narrowing the scope. And then if we consider that your parents don't have that disease, we're down to 70. And our aim at Genomics England really is to give back to the clinicians who've ordered that test as few variants as possible that could be causative, so that when the patients get that diagnosis, we know that it's built on a solid foundation. And to do that, we maintain an internal knowledge base called PanelApp. And PanelApp is available online. It's free to use by anyone in the world. And essentially what PanelApp is a mapping of genes to disorders. And so we maintain about 300 separate panels, so 300 separate disorders. And on those are lists of genes that we've curated evidence for so that they can be used in a clinically diagnostic setting. So what does a panel look like? We use a traffic light system to sort of categorize the level of evidence for these panels. So a gene with a green label has enough evidence to be used in a diagnostic setting. The amber and red genes, while there is some evidence that they're potentially involved in these disorders, don't have enough evidence. And internally, what we do is we have a very specialized curation team who spend all their time looking at databases, different sources of evidence, assessing them to see whether they can be used to promote genes that are either amber or red, or potentially even not on the panel, into the green, where we can actually use them in those clinically diagnostic settings. And one of the sources of information that we use is scientific literature. And that's great. However, the problem is that there's a lot of scientific literature. So if we look at the number of publications in 2022, that's about 3 million. So there's no way that a human is going to be able to keep tabs on all that information as it's coming out every year. And if we also want to go about building a sort of automated pipeline to be able to sort of go through this deluge of information, just you've got to think about the number of combinations, right? So 3 million articles, 20,000 potential protein coding genes, and 300 panels. We end up with 20 trillion combinations. So we sort of blindly went on this path of like, can we build this automated literature scanning tool? And so this was the strategy that we came up with. There is essentially like lots of filtering steps. There's trying to get rid of as much of the noise as possible before we hit the large language model, which is actually assessing the evidence. Because large language models, they're great, they're fantastic at what they do, but they tend to be quite slow. There's no way that we can feed 3 million articles into a large language model. And so step one is to essentially do a keyword search. The great thing about genes is that they have very, the way their names are formed is that they're not just likely to be just randomly included in a bit of text. I can't actually read it there, but if I look up there, we can see A2ML1, that's a combination of letters that is just unlikely to be randomly in the text. So from that, we can find mentions of genes in literature. We then take all the papers that are found from that approach, and they go through an embedding process. And similar to what is traditionally called retrieval augmented generation, RAG, we do a similarity search based on a condition. So for instance, intellectual disability is the one that we've been focused on. We then pull out all the papers from that subset of articles that are mentioning the condition. And then finally, from that subset, they can then be fed into the large language model to assess whether there is indeed a gene-disease association there. And the ones that finally pop out at the end get passed on to our curation team to determine if that evidence is in fact valid. The large language model is not directly updating to Panel App. We still keep humans in the loop. They are exceptionally valuable in sort of determining whether that evidence is in fact real. So this is the prompt that we sort of used for our proof of concept project, at least. And it's broken down into several different steps. The first step you can see highlighted in blue at the very top. This is quite often called the system prompt. It's essentially setting the scene. It's letting the model know what to expect in terms of the task. It's getting the model prepared to perform to its optimal ability. We then inject an entire scientific article, and we ended up using Claude for this process. And the reason we use Claude, essentially, is it just has this ability to absorb huge amounts of text, which a lot of the other models don't. Scientific articles can be very, very long. So that gets injected next. And then in the paragraph that follows is essentially lots of different things that we've tried tweaking to essentially augment the model's performance so that it gives us the best results possible. So for instance, in red, we can see that we've added even if it is inconclusive or not strong, because Claude, I think, assumed this is a medical setting, right? So I've got to be really cautious. I'm hesitant. I'm not jumping to conclusions. So we included that because ultimately we want our biocuration team to be the arbiters of the evidence, not the large language model. So genes also change their name over time. So quite often they'll have a whole history of different names that they've been known by. We don't rely on the model intuitively knowing that information. We inject all the aliases that those genes might have been known by. And our curation team is also interested in just primary sources of literature. They don't care necessarily about cited sources because the chances are that's already been assessed. So it's primary literature as it's coming in. And then there's a little trick you can do actually where you ask the model to think in XML tags first, and that has been shown to improve performance. And then finally put all the additional output that the model generates in answer XML tags, and that makes it very easy to parse, and you can just pull out the bits of text that you really, really care about. And so we applied this to our intellectual disability panel. This is one of the most widely used panels in the genomic medicine service. It feeds into lots of other panels as well, so this was really a target for us. And we ended up really on a narrow focus, right? Can we just promote even one gene from that red sector, which is about a third of the pie, into the green, right? So that is now used in a clinical setting. And for speed purposes, during the proof of concept stage at least, we really limited ourselves to genes where we'd found about 100 papers for, just because like the models at that point were quite slow. I actually want to skip that. So this was the first paper that we found, and this was actually really exciting because this paper allowed us to take this gene, which had been previously labeled red, to green. So this was now being used in a clinical setting. If a patient comes to us, gets sequenced, and has a mutation in this gene, and they've been sequenced for an intellectual disability, this will now be directly fed back to the clinician so that the patient knows potentially what has been causative of that. And the really cool thing about this paper, I think, is that if you look at both the title and the abstract, there is nothing really that would hint that this is a paper that is going to be able to do this. And I've highlighted in red the one sentence in the abstract which is pointing to the fact that this might be about intellectual disability. And that's skin-derived fibroblasts of two unrelated individuals with neurodevelopmental disorder, et cetera, et cetera. And the reason this is difficult is that neurodevelopmental disorder means so many different things, and actually it doesn't necessarily apply to the intellectual disability panel. We have several panels that this could be related to, and so this was a really exciting find for us. And what did Claude have to say? This is the summary that it generated, and again, actually the one key point of this summary is the final sentence. Further studies would be needed to conclusively demonstrate causality. So again, Claude just being a little bit too cautious there. What we found was that this this particular article, if we ran it through the model several times, would only give us a result about 50% of the time. And this led us to a very nice conclusion, actually, that we can use this almost as a confidence score. So an article that only came back about 10% of the time, it's probably not likely to be very good evidence. But if it's coming back 90 or 100% of the time, and this is probably going to be good evidence, so when we feed this back to the curators, they know roughly how good that paper is going to be. And so from our first round of analysis, this is on about 350,000 articles, we managed to promote 3 genes from red all the way to green, so those are now used in a clinical setting. 1 went to amber, and then of the articles that we found and passed to the curators, quite a few actually of them stayed red. But the largest section of that, the 7 at the bottom, they were valid evidence, it's just the curation team had already found them. So that's the problem with using a retrospective data set. The curation team were already on their game. So the next step essentially was to think about whether we can take this into more of a production setting. Can we do like live scanning of the scientific literature as it's being published? And actually, do we even need to, right? Like how well are the curation team doing at being able to pick up articles as soon as they're coming out and then including them in Panel App? And we can do a bit of analysis where we look at the time of publication and then the time the article appeared in Panel App. And what we found is actually that lag is about 2.5 years. So from the cutting edge of genomic science to actually going into practice is a lag of 2.5 years. And if we can surveil the literature as it's coming out, then potentially we can bring that lag down to maybe less than a month even. So as soon as something is newly discovered, it's put into practice. And to do this, we've turned to Europe PMC. It's a huge repository of scientific articles, indexing about 9 million articles to date, and you get about 10,000 articles per week with this. And we've also updated our prompt to be a bit more beneficial for sort of a more scaled up environment. So for instance, now, instead of that just generate me a summary, what we're doing is asking Claude to essentially make a JSON structured output in the schema above. Ooh, the lines have moved. And also pulling out bits of information that the curators really care about. And from that, we can generate essentially a nice big Excel spreadsheet, which we deliver to the curation team every week. They go through it and assess how those articles to see whether they're any good or not. And this pipeline sort of went live at the beginning of last month. And so far, we've found we've delivered 18 papers to the curation team as of the 23rd of September. And 7 of those seem likely to lead to gene promotion after an initial triage. 2 were for genes that are not on the panel at all. So these are completely new associations that have been dug up from the scientific literature. And then 1 was considered to be a good paper, but it just wasn't relevant to the panel that we were investigating. And then finally, 1 gene has gone through the entire curation process and has already been recommended from promotion from amber to green. So again, any patient who gets a mutation in that gene will now be fed back to the clinician. I'd like to thank many people who've been involved in this work, particularly the curation team. So Eleanor and Arena from the biocuration team. Without their support and feedback, there's no way we would have been able to do this. And we were actually working in collaboration with the AWS healthcare team. So Lou Warness and Chemra Azor were directly involved with this project at all stages. And yeah, thank you very much for your attention. It's been great to be here. Thanks to the organizers. And I'll be around, I think, in the other room afterwards. Cheers.